Okay, so earlier this week there were a lot of problems with the monitor, and I'm very glad I recorded our lecture before spring break because everything was messed up, and Sherry couldn't write on the screen for the 2-2 aiders and stuff, so it was a mess. Looks like it's working good now. Hopefully, keep your fingers crossed. You guys had a high of 98, woohoo, on exam 4. The mean was 60, so the average was 60. So if you got a 60, that means you're sitting on a solid C, okay? And the mean has been around 64, give or take, on most of the exams. So if you're sitting around that 64 area, you're a solid C. If you're above that, you're looking at a C plus, B minus. It just depends where the curve will end up being later. If you're below that, same thing. You might be a C, you might be a C minus. You could even be in the D, like D plus D region. But I won't know where those parameters will be set until after you guys have taken exam 5. Once you take exam 5, it gets set. And then we'll post on the A&P site. When you type in your grade after exam 5, you'll be able to see what your grade is. And it'll give you further instructions on how to determine what you would need to get as like a minimum on exam 6 to get the grade you were hoping to get. But if you guys have been following through, like I said, I haven't put, these aren't, it's not like the curve is set for each individual exam. The curve isn't set until the end. When I post the mean and the average and stuff, I'm just letting you guys know where are you sitting right now in regards to how the rest of the class is doing, which will give you, it's a good indicator of when the curve does get set. It's usually right on that same region. Yes?
I think that's Norway 9 and that message that's on there. So the lab practical, it will have me and a high and
yes. So after you guys have taken the lab practical, I'll post for any exam, that one included, where the high was, what the mean and the average, the mean is the average, but what the mean and the median is for that exam. And then, so you guys will probably know those scores by, I don't know if Sherry will get a chance to run because those are a Scantron exam. I don't know if you'll know what that exam score is until maybe after, but it might be that weekend, and at the latest it would be Monday, because the last class to take it would be the Friday evening class, and Sherry doesn't hang around late Friday, so, but she may come in on the weekend, run the Scantrons, and as soon as they're posted, I will make a post like that, let you guys know where you're at. And then after exam 5, I let you know what the average was for that exam. And then when you guys enter your grade in, at that point, you'll see a letter grade when you type in your student ID number to see what you're getting. And that, then you know, then the curve is set. And then you'll be able to see, and the points will be broken down, and it'll tell you how to calculate how many points you'd need to get on exam 6 to get a blah, blah, blah grade, okay? Also, if on the A&P website, if you go under on resources, I think in one of the middle columns it says the curve. You can click on that, and it's a YouTube video that Peter Zao had created when he was still teaching here to explain what how the curve works and what it means. So you can view that. It's not too long. We finished up chapter 13 on the recorded lecture. We're moving on to chapter 14, which is the PNS, or peripheral nervous system. And you guys, we've talked about some of these things. The nice thing about last lecture as well as this one, we keep building on material that you guys have already learned. And so we briefly talked about the peripheral nervous system, and here's the breakdown. So peripheral nervous system, it provides the links to and from the environment to our CNS. And what's your CNS, the main component? The brain. I mean, you're going to come up the spinal cord to get there, but brain and spinal cord is your CNS. So it's allowing the CNS to receive the information, which is the sensory, the afferent, the ascending fibers coming in, right? And then carry out the decisions that was made by the CNS. So your brain processes it and decides what should we do with that information that I just received. And so that would be then the motor, the efferent or descending pathways, okay? And even though that's a very simplified version, I think I was probably a little confusing when I drew my diagram, and I'm going to simplify that a little bit more for you guys today, but as you hear more information today, it'll make more sense, and you can draw the same kind of diagram that I drew last time and look at where the fibers would come in, Who do they communicate with? Do they talk to another neuron, like an interneuron, and then they come back out? So we'll definitely be talking about the DRG or dorsal root ganglion today. So I think it'll make a little more sense because you guys were probably a little confused. I confused myself. I was like, why did I say that? Okay. So PNS links CNS to the body. The body is essentially a complex life support system for your brain, which is designed to give the brain sensory information. So sensory, like we said, is the afferent division or ascending pathway. Let's do that and that. Ascending pathways. And you guys have heard me say these terms over and over again. So if you are still confused by the terminology, you need to go back and make yourself understand it. Repeat it, review it, because you guys might be feeling lost if you don't know what the terms are. It's like learning a new language. If you don't practice the vocabulary, you're totally lost when the teacher's giving you new vocabulary to add on to it, right? So motor, the efferent division would be called, what other name for it, pathway-wise? Descending and, okay. And ganglia, so these are collections of cell bodies in the PNS. So remember briefly before we talked about whether something's a CNS or a PNS. So this chapter is all about the PNS side of it. How does the PNS then communicate with the CNS, okay? So ganglia, PNS. And what do we call a collection of cell bodies when it was the CNS? Nuclei. Nuclei was CNS, ganglia are PNS. Okay. So in this diagram here, they grayed out CNS because we're not really going to focus on that aspect of it. We're going to talk about the PNS, and then that can be broken into two divisions there. So you have the sensory or afferent division, and you have the motor or efferent division. Okay, and that can be further divided again to the motor efferent can now be the somatic nervous system, and that's what we used before to control the skeletal muscles, okay? And the other side of motor would be the ANS or autonomic nervous system, and that would be what controls the heart, smooth muscle, and glands. So this is all a review of stuff we talked about, but you might have forgotten some of this because it wasn't so important on the last exam maybe, or we briefly talk about it and we just keep adding to the story. Then the ANS, autonomic nervous system, remember automatically it happens. Do you control your heart? No, so that's why you think autonomic, automatically happens. ANS, it can then further be divided into sympathetic and parasympathetic. So sympathetic is, do you guys remember the silly terminology we put with that? Fight or flight, right? That's your survival mode, essentially. And parasympathetic is relax, rest, digest. Can't digest things when you're running away from the bear. You have more important things like surviving. So let's talk about the sensory receptors. So most of the neurons we talked about were multipolar neurons, right? But now when we're talking about sensory receptors, what kind of neurons are the sensory ones? Unipolar, right? Remember it had the branch coming there, and we said it's almost kind of like it gets tied off with a ponytail, and people argued whether you have the dendritic side versus the axonal side, and in reality they said, you know, it's kind of both ways information. So that's the unipolar neuron that looked like this. That's what we're talking about on sensory. And where did we say his cell body lives? Where does that little head live? His cell body lives in the DRG, dorsal root ganglion, okay? So sensory receptors are our most simple receptors. They're very specific with the type of info that they take into the brain, which is your CNS. So for example, if you had a thermostat in the house, it's specific for temperature, right? Nothing else. And so will it monitor CO2 in your house? Not unless it has a CO2 monitor associated with it as well. So if it's just a thermostat, it's only measuring temperature changes, that's it. So this is way back even to first week or whatever that we talked about stuff. So these guys are very specific also. You're going to have a sensory that's only for hot versus cold. You're going to have a sensory that's only for light touch versus deep touch. You're going to have a sensory that only detects vibration, nothing else. That's what we mean by they're very specific. And let's see, sensation versus perception. So when we're talking about sensation, it says the CNS awareness of stimuli. These may be subconscious. So what do we mean by subconscious? You're not really thinking about it. It's like in the background. Do you remember when we were talking about the RAS? And we said, you know, you could be driving and then all of a sudden you're at your location. You're like, I don't remember how I got here. I hope I safely drove here and stopped at all the red lights and stop signs and same kind of thing. You were getting this stimuli. You were driving. You just weren't paying attention to it. And maybe in your subconscious, you were doing all the motions of doing the right stuff, but you know, so that's what it's kind of talking about there. So sensation, awareness, subconscious, you're thinking the RAS part of it. Perception is the conscious interpretation of the stimuli. So the difference would be sensation means that the stimulus was sensed by the receptors and the info got in, right? You still got information in, but what did the RAS decide to do? Turn the volume down if it wasn't important, right? It didn't have to tell you your shirt was touching, your shirt was touching, your shirt was touching you, the chair is hard, the chair is hard, the chair is hard. You're constantly getting that information, but remember, we filter out like 99% of that info. That's the subconscious part. So you still got all these sensations were being stimulated and you're getting signals, but the RAS said, not important. Turn that down. We don't have to pay attention. But if there's a change or something happens and now you perceive something, right? Maybe that perception is I brought it to your attention and now you're thinking, why'd she have to tell me the chair was hard? Now I know it's hard and I'm paying attention to it being hard. So perception is where the RAS helps determine this part, and the RAS makes you aware of the event or the stimulus, okay? So that's the difference between sensation versus perception. And let's see, classification by stimulus types. So we have classified by what turns the receptor on or by what the receptor is designed to respond to, because we said they're very specific. So we're going to go through a couple of these specific stimuli. We have things called mechanoreceptors. They respond to mechanical force. And so what we mean by that is, I used the term mechanical deformation before. So mechanical deformation. And you could, an example of that would be you have specific mechanoreceptors just for pressure. You have mechanoreceptors that are just for touch. You have mechanoreceptors that are just for stretch. And sometimes a combo like pressure and stretch can sometimes both be with touch, because if you push against something, you're deforming what your finger looks like physically, right? And then at that time, you're getting a sensation that you have pressure pushing up against your finger that you're mushing down on the hard surface or table or whatever. And then also, if I'm mushing down, am I also not maybe stretching other things around there? So that I could have a couple different mechanoreceptors right there giving my brain multiple signals saying one is being stretched, one is having pressure against it, I am touching something or something is touching me. So if we look at thermoreceptors, those are pretty easy, temperature. So they just detect how hot or cold something is. Where would you maybe have a thermoreceptor? On your skin, right? You can feel if the room is really hot. You can feel if the room is kind of chilly. You can feel if you're touching something hot or cold, that kind of thing. Photoreceptors, what do you think that one is doing? So it's detecting light. And where might you have photoreceptors? In your eyes. Rods and cones, they're photoreceptors. And we delve into this a lot more when we get to 228, when we start talking about special senses and how your eyes perceive light and what's going on there. Chemoreceptors, I know this sounds kind of weird, but chemo means chemical. So these are receptors that detect chemicals. And where do you think you might have chemoreceptors? In your mouth. So things that you take into your mouth, you think that you're eating just food, but they're various chemicals, right? And so you can taste different things, smell different things, okay? And a lot of your taste has to do with your smell. And both taste and smell are part of your special senses. Again, we'll talk about the details of that in 228. But those all have chemoreceptors. And then what do you guys think nociceptors are? Kinda. So nociceptors are pain receptors, essentially. Okay, so this is PN for pain. But almost all of those other receptors, a mechanoreceptor, a thermoreceptor, a photoreceptor, a chemoreceptor, any one of those that you get enough stimuli could become a noxious stimuli. Noxious meaning bad, icky, you don't like it, painful. So any one of those, if you had too much heat, a thermoreceptor could become a nociceptor, right? Because it's too hot and you burn yourself. So it's trying to tell you, this is getting hot, you really need to stop. This is painful hot, you're going to hurt yourself if you don't get your hand off of that, so on and so forth. Or even certain smells could be noxious, right? Have you not smelled a smell before that was so disgusting you literally thought you were almost going to vomit? If you've worked in a hospital, you've had to have at least smelled it once. There's always something. For me, gangrene was one of the worst smells I've ever smelled. It permeated the whole first floor of the hospital. You could not get away from it. Other people have said, like when they've done certain abdominal surgeries, what do you call it, in the intestinal area, can be pretty rank and stinky. And the smell can be bad enough that it can make you sick, right? Even technically, I guess you could probably even say when some people have migraines, and let's say certain smells or things can affect them, then it's definitely become a nociceptor, right? If they're sensing a smell that's making them ill, giving them a migraine, they feel nauseous, sick. So that's why we're saying any of the other receptors, any of those receptors can be a nociceptor if the stimulus is strong enough. Can be a nociceptor if stimulus is strong enough. Okay. Just trying to spell if, and I was thinking of is and the S. There we go. So pain's a stimulus for nociceptors. It's important for survival. We need to know if something is hurting us, but keep in mind that any of those receptors could end up becoming so stimulated that they're not just a mechanoreceptor, but now they're acting as a nociceptor. So this could be the difference between if somebody's lightly squishing or touching your finger, right? You're compressing it. That's not painful, but you are getting the mechanoreceptors are being stimulated, sending that signal to the brain, versus if somebody crushed my finger, that mechanoreceptor is now a nociceptor because that would hurt like a right? We don't like that. So that's why it means any of those above receptors could be noci. Classification by location. So this is talking about either it's from outside of our body or from the inside of our body. So extero, what do you think that means? Exter, external, exit, think sensory, a sense, external sensations. Intero receptors or visceroreceptors. Do you guys know the term visceral? Visceral, you're thinking organs. Organs are inside. So that's why interoceptors are visceroceptors. So these sense internal sensations because of the organs. So if we go back to extero, these external sensations, these can be touch, pressure, pain, temperature, stretch. Okay, any of those that you would experience from the outside touching your body, and your body could sense those outside stimuli, that's an exteroreceptor. An interoceptor from internal, these are going to be things like pain, pressure, stretching. So for example, when your bladder fills with enough fluid, it stretches. And those stretch receptors give a signal to your brain that it is time to void your bladder or go to the bathroom, or you'll be doing the pee-pee dance, or you'll have an accident, right? So that would be an interoreceptor, right? It's internal to the body. It has to do with viscera, it's organ. Now, some things on the inside of your body are hard to pinpoint, right? So for example, sometimes people have had gas in the intestinal area. And if you haven't ever experienced it, gas can actually be extremely painful. And your brain doesn't know what's going on. It just knows there's some discomfort here and it's really icky feeling and you're starting to think, I'm dying, I don't know what's happening to me. Because people don't think gas can be that painful, but it can be a sharp pain. It can be very uncomfortable. And again, hard to pinpoint, but oftentimes internal type of receptors as the pain gets further along. So for example, if you had appendicitis, most common people will get diffuse pain, meaning that's kind of all over the abdominal area. And they're thinking, I don't feel so great. I don't know what's going on. Next day, it might hone in a little bit. Third day, you might only be tender near the appendix. And out here isn't as tender as it was, but if you touch there, you're coming off the table, and then your body's slowly pinpointing where are these signals coming from. So that's why I mean it was diffuse before. It doesn't know. Something's weird. Something's not quite right. It doesn't feel great, and it's getting worse and worse. Hello, body, figure this out. So these interoceptors are not as precise as the exteroceptors. And then the next part of an interoceptor is we have something called proprioceptors. So this is information going to the cerebellum about your body position. So you guys remember before I talked about body position and cerebellum, and I briefly said proprioception, and sometimes I forget that you guys don't know what I'm talking about yet because it's further on in the notes and I'm first introducing it to you. So now you guys have heard it a couple times. Proprioception, think cerebellum, and it tells you these are going to be located in your muscles and tendons, and you have things like muscle tendon organs, like Golgi tendon organs, things like that, that they are interoceptors, and they tell the cerebellar peduncles to take that information to the cerebellum. Do you guys remember which cerebellar peduncle from exam 4 material? Inferior cerebellar peduncle would take this information from these proprioceptors to the cerebellum. Okay. All right. Good, good, good. Let's see. I'll write that there for you guys too. Inferior cerebellar. I'm just going to put PED for peduncle and make it look like I can actually draw. Okay. PED. All right. What else do we want to talk about? Oh, we can classify by the structural complexity. So if it's something simple or is it something more complex? So most are going to be simple. And they're found throughout the body, and they monitor general processes. So that makes sense that if it's simple, think basic, think general process. Not super good at what it does. Doesn't have all that fine tuning. Versus complex means that you're probably getting multiple things that are giving you information. So the structural complexity being complex, and these are your special sense organs. So when we get into 228, we're talking about how the eyeball works and how all the different cell layers that the light travels through, and it stimulates here and it travels there. That's a lot more complex than something that just, a general process might be. Okay, so so for complex, this is going to be like your eye, so your vision. It'll be hearing and balance. So who does that? Has to do with the ear. Even your ear has to do with your balance. Okay, cerebellum has to do with balance as well, but for special senses. And then nose has to do with your smell, that type of thing. So those are all complex. Let me do this so that you know this all goes under complex. Okay. And again, these are not the majority. Simple is the most common one that you're going to note. So what else? What would be another name for a proprioceptor then? Let's review. It's right in front of you. Interoceptor. Yes, it's an interoceptor. All right. Moving right along. Simple sensory receptors. Let's see. Which are tactile, right? You guys know the term tactile? Kind of like having to do with touch, right? So Since we're not going to talk about complex this semester, that's more 228 information, this is now kind of going on, we're simple. So where we're saying the simple classification, simple complexity, this is where we're unencapsulated and encapsulated are simple sensory receptors, okay? So they're differentiated by the amount of CT covering them or around them. So non-encapsulated would mean, or unencapsulated would mean little or no CT around it, versus encapsulated is telling you that there's going to be more CT around it. And we find these unencapsulated or free endings in the epidermis, and we find the encapsulated ones in the dermis, the deeper layer, right? And what else do I want to tell you? We're not going to go into the details of the different kinds of, you might have seen it in like your lab manual when they talked about like the Merkel's discs and different sensation for touch. We're not going to go into that much detail in lecture right now. So unencapsulated is going to be no CT around the receptive end. What's the receptive end of our neuron? Dendritic, yes. So no CT around that dendritic end. Encapsulated would mean that we do have a CT capsule around the dendritic receptive end, right? So we do have CT around dendritic receptive end. Okay. And let's see, proprioceptors. Proprioceptors report body position. That's what we talked about earlier, right? And so these are encapsulated. And a couple of examples that we're going to go through is muscle spindle, which reports skeletal muscle stretch, okay? So for example, if you contract your biceps brachii muscle, right? You contract it, you end up stretching the opposite muscle, okay? The tricep muscle, this gets stretched because you contracted here, but this guy had to get stretched. There's stretch receptors there telling your brain that I just got stretched a little bit. So part of this is a protection mechanism. If somebody wants to close that door, they're kind of loud up there. So part of this is a protection mechanism because if the muscle was stretched too much, what could you do? You could tear it potentially, right? You could damage yourself. So these are supposed to tell you, wait a second, we're getting stretched just a little bit, this is fine. Okay, we're getting stretched a little too much now. What are you doing? Okay, this is going to get painful in a second, and I don't want you to get hurt. Okay, that's what your body's trying to tell you. We also have Golgi tendon organs, which I said a second ago, and those report tendon stretch. And then you have joint kinesthetic receptors, which reports joint stretch. So for example, with proprioception, when you see people, if you get a chance, you're kind of watching like a group of people. So this might be people standing up for a while, so it could be at a wedding. You know, people are up on the stage for a while. Could be at like a church thing or something where people are kind of gathered and everybody's standing for a little bit. If you watch, you'll notice that people slightly sway from side to side. They aren't really aware of it. They think they're standing just straight. But what happens is they start to lean to one side. Their brain is getting signals in the joint, in the Golgi tendon organ, in the muscle itself that are sending signals to the brain that you're starting to lean too far to one side, to the left, let's say. So the right side will say, hey, you better contract and bring them back to midline or they're going to tip over. So then your body understands your position sense from getting information from those sensory receptors, and it'll bring you back midline. And then you might go a little too far, and then it'll bring you back midline again. So back and forth, this kind of happens. But it's nice to watch when you watch people because they don't know they're swaying that much. And it's sometimes not as perceptible as it is for some people. Let's see. And these names tell you where to find them. So if they say muscle spindle, you're talking about skeletal muscle, right? If they're saying Golgi tendon organ, it's telling you it's in the tendon. Joint kinesthetic receptor, it's telling you it's in the joint. So they made it easy for you on those ones. So that's nice. And let's see what else do I want to tell you about it. Another thing with joint kinesthetic receptor, let's say if you closed your eyes and somebody pushed your finger downward, your joint is sending signals saying your joint is in a different position. And you would be able to tell whether it is now downward versus upward. Does that make sense? So somebody can move like your whole finger, and you would know with your eyes closed because you understand what that sensation means and what that joint sensory receptor is telling your brain right now what's happening. That's what it's describing there. So overview from sensation to perception. So now this is trying to put it all together. This is a little bit of that diagram I tried to draw on the recorded lecture, and you guys were going, what is she doing? Oh my gosh. Please step away from the console. So this is kind of where it's separate. Instead of a simple spinal cord drawing, this is just showing you like different layers, as if you were in the spinal cord here, and then this neuron now talks to this neuron here and has a synapse, and then how it eventually gets up to the brain, because the brain is where you have your conscious. The CNS is the conscious part of it, right? Okay, in the cortex, that's where you are thinking and making decisions. That's your conscious part. So 3 processing levels in any sensory system. You have the receptor level, which occurs at the level of the sensory receptors. You have a circuit level, pathways leading to higher level processing circuits. And you have perceptual, which is the complex circuit that allows us to form perception. All 3 areas must be intact and fully functional for perception to occur. So if you don't have a receptor to send the signal to the brain, you don't know what's going on, right? You have nothing telling you that you've sensed anything. If the receptor is fine, but the circuit level has problem with it, it didn't make it to the perceptual part. So you still didn't know that something happened. If the receptor is fine and the circuit is fine, but the perceptual part of the circuit is not working, then you don't know how to interpret the information, right? So that's why it says all 3 of those have to be intact for these processes to make sense and you to be aware of it, to perceive it, okay? So here we have our little brain. We have our spinal cord at the bottom. This is kind of a review of some of the exam form material. So remember, this area right here is called what? Do you guys remember? What part of the brain is that? The dotted line that I drew on the CNS part. It's not in the CNS, but diencephalon, okay? And the diencephalon includes the thalamus, okay? Remember, the thalamus is your sensory relay station, your triage center. Everything's got to go through this area and talk to it so that you can make sense of it. Ha ha. Okay. Then we have our midbrain area, and that's talking about the brain stem. The pons is just talking about like fiber tracts, so it's not so important on this picture. That's why they didn't include the pons on the picture. We have our medulla oblongata, which is, remember we said that things have to decussate. So this is an area where it might cross over. Decussate means to cross over. So remember, information from your right leg is going to cross over at some point, and then it's the left side of the brain perceiving that sensory information. This is that term decussate is what it's talking about there. And so in the, we'll come back to that. At the bottom here, you have your spinal cord. So that was the little picture I tried to draw before. So I'm going to cut out some parts so that it's not so confusing to you guys, but I had a little bump there and it comes in here. And I'm just going to draw a generic kind of circular thing. Here's my central canal through my spinal cord. And remember, I have kind of like a little butterfly looking thing here. What's the butterfly made out of? What kind of matter is the butterfly? Gray matter. Okay. So, and there's another nerve on the other side. They didn't draw it on either picture. I'm just trying to make it simple. So you have another DRG on the other side. So this was your ventral horn. Ventral meaning this is the ventral side of your body. This is the dorsal side of your body, the back. Think dorsal fin, right? Back here, this big bump, what did we call him? The dorsal root ganglion, so DRG. I took off the little dorsal rootlet off, so not to worry about that, so that we don't confuse anything. And I also talked about, I'll add it to the picture in a second. Let's just leave the spinal cord like this, kind of basic for a moment. So with the spinal cord, then we had what was our primary neuron coming in. So what they're trying to talk about on this picture here, primary neuron, that's the purple one here. And remember, you have a purple, I'll try to keep I don't think they have purple for the colors. I'll do blue. So purple neuron coming in, those are the receptors for proprioception, discriminative touch, precise pressure, vibration. I'll talk about those in a little more detail in a moment. But these are all sensory, right? And you guys know sensory comes in. These are afferent fibers, ascending, going up to the brain. So here is my my sensory nerve, and his cell body resides where? He's a unipolar neuron, and he resides in the dorsal root ganglion. So there's his little roundy nerve cell, right? His cell body. And then his neuron continues on into the dorsal horn of the gray matter there. Okay, so that's sensory. Sensory information coming in for the most part is going to be on the dorsal side, information-wise coming into the brain. So what's typically going to be on our ventral side? Motor, and we'll talk about that in a second. So let's see. So the picture on here, they're saying anterior root. Another word for that would be the ventral root. The posterior root would be, another name would be dorsal root. Okay. What else do I want to tell you? I might as well go into, you guys won't need to know the terms fasciculus gracilis or fasciculus cuneatus or the posterior funiculus. What we were calling them and what I did on the picture before are dorsal columns. So instead of calling them these guys, oh, let me put that back in another color. These are your dorsal columns. And so on one side, this would be like a dorsal column, and then they have one on the other side. So back here, this is the dorsal side of your brainstem. I'm sorry, not brainstem, spinal cord. And so on one side, this would be like the dorsal horn. And on this side would be another dorsal horn. The dorsal horns are in what color matter? The white matter, okay? The lighter side of your spinal cord. So did you guys realize in the cortex, in the cerebrum, you had gray matter was in the outer part, white matter was on the inner part? It's like the opposite in the spinal cord. You have gray matter central, and you have the white matter external on in relationship to each other. So, so those are the dorsal columns. They will take the proprioceptive, discriminative touch, vibration, etc., the very specific information. Eventually, it'll come up to our primary somatosensory cortex up here. So if we follow how it gets up there and stuff, so you have your primary neuron. He's then, this picture didn't show him talking to another neuron, but I drew another interneuron before. And mostly the simple picture I drew was just, let's do, well, let me do green. So on here, I did a neuron here, and he was my interneuron. And then I drew another neuron for motor where I said he'd be here, and then he'd come out and be effector, so motor, right? So that was a very simple circuit, if you will. This picture is showing it slightly more complex because they're saying instead of just doing like a reflex circuit there where you might not even talk to the brain and tell it what's going on, ouch, that's hot, pull away, or when people check your reflexes when they bang your patella tendon and they want to see your leg kick up and see if your reflexes are intact, it doesn't communicate to the brain that you've done that. It just does it. It's a reflex. This is more like a reflex, a very simple, think caveman style, okay? It's basic, simple. This picture here on the left that their diagram is the more complex way, and it's what actually happens with the other parts. So we're going to follow up this pathway now. So instead of their interneuron being green there, they took their interneuron. They didn't make it happen until they got up here to the medulla oblongata. And then it talked to an interneuron, which they did in blue. And so their interneuron was here and went up through the midbrain to the diencephalon to synapse with somebody that was in the thalamus. So once they synapsed with the thalamic one, he went up and then he synapsed and talked to the primary somatosensory cortex in the postcentral gyrus. So a lot more complexity to that, right? But if you understand that you have sensory coming in, it's going to talk to another neuron, the intermediate guy, the middleman, the interneuron, and then the interneuron is either going to go up to the brain and talk and get information, and then he'll send information down, and eventually that other information coming back down would then talk to the motor side going out, the red line I drew on my diagram. So I only drew like a really simple picture there. I hope that clarified what I confused you guys with the other day, maybe? Maybe not. All right. So the interneuron is what they're calling as the secondary neuron right here, is their interneuron, okay? So that synapses in the thalamus, and that's going to synapse with another neuron, which is your tertiary neuron, is what they're saying here in the picture. Tertiary neuron is the one that then will go to the primary somatosensory cortex, right? When we were talking about columns, so I'm going to come back to that for a second. So we said we had a dorsal column. You also have a lateral column, which will be on the lateral side of things. And then you also have an antero or anterior column, which would be kind of in this area here. So I'll just draw it on one side on mine. Oops, nope, don't do that. Okay, and then it had a lateral column here, and then it has kind of an anterior column there. And it's like we split it in half. So you have an anterior column on the other side, a lateral column, and a dorsal column on the other side of the spinal cord. And sometimes you're going to see a term in a minute, anterolateral. So what do you guys think that means? Kind of both, right? Kind of in between, going in partially anterior, partially lateral, or we're talking to both of those areas. So I just wanted to point that out here because you're going to see anterolateral in a second. I wanted you guys to understand it's kind of talking about like there. But now you guys know when they're saying a dorsal column, and these are all in the white matter in the spinal cord, okay? So what else do I need to tell you? So if we look at what happens at the receptor in order to initiate the entire pathway up to the brain for us to have perception. So that was the pathway physically that you could see with the diagram. Now let's talk about how do we understand that information and perceive it. We look at processing at the receptor level. So we have transduction, which is converting the stimulus to an electrical potential. So when we say stimulus, this could be a chemical stimulus, a temperature stimulus, a mechanical stimulus, and we're going to convert it into an electrical potential. So for example, physical thing happens to you, and then you will change that physical stimulus to an electrical event. You guys already know all about this, right? You got some sort of sensory receptor. The axon was down there, or the dendritic end, right? Sorry, dendritic end, because it's sensory, has sensed something. You touch something, it's hot, it's cold, whatever. What did you do with that information? You created an action potential. When you had enough of a stimulus that you reached threshold, you created an action potential that went down the whole axon, right, and sent that information. Because it's sensory, it's unipolar. That's why it's a little different than what you guys are thinking of your traditional dendritic end to axonal end, but it's the same process. You created an action potential, an electrical event, right? An electrical event. You depolarized your cell. You caused it to change. You might have opened and closed other gates and then reset it and go back to your resting membrane potential and stuff, but you guys already know all of that. That's what it's talking about, converting a stimulus to an electrical potential. Receptor potential is a graded potential is produced. So you guys know a graded, yes?
If the electrical is same as voltage, would it be considered the same?
Yeah. I'm going with it, yes. Yes. So the question was, would voltage be considered the same as an electrical change? And I'm saying yes, think of it that way. Yes. Yeah. So receptor potential is a graded potential. And you guys remember graded meant not quite, right? You needed kind of multiple ones to do it. Well, things are a little different here when it gets to the spinal cord and the brain. So when you have the graded potential, let's talk about generator potential first. So generator potential occurs when the sensory receptor has gotten enough stimulus to reach threshold. And before, you guys knew that it had to have been, usually it was a change of 15 millivolts to get you to the negative 55. You went negative 70 to negative 50, right? 55. And then, yes. Sorry, I have old info in my head, stuck in my head from the old info, sorry. So you have the positive 15 millivolt change to bring you to the negative 55, and then that then allowed you to get your action potential, right? So threshold value means action potential, AP, action potential. So when we reach threshold with a neuron, the neuron fires. Threshold was measured at the axon hillock, remember, because that's where the actual action potential would get generated then. And we don't have an axon hillock with these guys. So at the receptor end. So everything is at the receptor. Okay, so whenever we get a generator potential, we will always get an action potential in this sense. This is different than the other neurons we had talked about. Okay, an action potential is still all or none. Nothing changed about the idea of what an action potential will do. Okay, it's just we don't have an axon hillock now because we're talking about our unipolar neuron. Okay, so also the stronger the stimuli, so cause the delivery of more impulses per second to the brain. So action potentials are always what? They always end up hitting what mark? If we were to diagram it out and we said the action potential did this, right? This level was what? How many millivolts? It was positive 30 there, but it was a change of, I should say that better, a change of how many millivolts? 100 millivolt change. From negative 70 to the positive 30 was a 100 millivolt change. So every time it hits that peak, it's had a 100 millivolt change. And so depending on, so this would be like a static event of it occurring. If you added more frequency, you'll hit that more often. Does that make sense? Closer together with your peaks. It doesn't go above that. It's not going to be like positive 50. It's still always going to just hit the positive 30. 100 millivolt change is just with the frequency, you get more stimuli. Remember we said the more stimuli, it could become more maybe noxious potentially. It could end up being a nociceptor, being too hot. It's because you're getting more and more stimuli, more and more action potential sending the signal to the brain. That's what it's talking about. So you would have closer together peaks that are still, pretend those are all the same height. Closer together peaks, more stimuli. I'm not sure if I'm losing some of you guys. The action potential is the same. You're just having them closer together. It's always a 100 millivolt change. That's what I'm trying to say. Does that sound better? Yep. Okay. So stronger stimuli, that's what it's talking about there. And let's see. So the magnitude will not change of the height of that peak. That is always just going to hit the positive 30 and you're done. Then you start to repolarize again. Let's see, processing at circuit level. So we have three main routes to reach the sensory cortex. We have the spinothalamic tract, the dorsal columns, and the spinocerebellar tracts. So you guys saw some of this on exam 4, right? I think. Or maybe I just read ahead. I don't remember now. Okay, maybe you haven't seen this yet. But it tells you exactly where it's located. Spinothalamic. Where is it going to and from? Spinal cord, thalamic, to the thalamus. Super easy and obvious on that one. These actually are found anterolateral columns. So now you know where anterolateral was, right? So these are non-specific. This is important. Non-specific information. So these are difficult to localize, and they're actually used by many different receptor types. So spinothalamic are non-specific. Okay? Versus if you talk about dorsal columns, dorsal being posterior, that's specific information, but it's only used by a few receptor types. Okay, so spinothalamic, these are the non-specific common ones. What kind of info do you think we'd be doing with non-specific?
Like the shirt one.
Could be the shirt one. We got pain, we have temperature, right? It's not super pinpoint. It's not like my elbow is at 98.2 degrees, but my wrist is at, no, it doesn't, it's not quite that good, right? It's more diffuse, more general with that, right? So we have pain, we have temperature, we have something called coarse touch. Do you guys know what that means? Not very refined, not very specific. It's, think rough, you know, like you grab somebody versus you gently touch somebody. That'd be like a coarse touch. And pressure. Okay, so those would be spinothalamic, non-specific types of sensory information. The dorsal columns that we said are going to be more specific. So this is going to be what we would say discriminative touch. Discriminative meaning you're more discriminating on what you are sensing or understanding. So like somebody saying, oh, I don't care what color you use when you draw in there, and somebody else would be very specific. I would prefer that you use the color blue and only blue and don't use anything else. I'm being more discriminative on my choices, right? So this is discriminative touch. D-I-S, criminal, no, just kidding. Criminative touch. Okay, and also vibration. You guys can sense vibration pretty good. You don't always realize it because you haven't probably really thought about it. But if you had your hand, oh, I know, like Jurassic Park movies, right? And they always have like the water glass and you could see like the boom, you know, when the dinosaur like clomps by and they see the water vibrate and stuff. So if you were sitting somewhere, let's say you're sitting in the car, you could tell whether the car was on and you were traveling or whether you're just sitting there. You'd feel the vibratory sensation of moving along, right? Or if you put your hand on a speaker, I want to say old time speaker because you don't really see big speakers anymore, but you put your hand on the speaker, you could feel the vibration of the sound waves, okay? You could feel it on your skin. You can feel that. And I don't know, maybe this is like a caveman thing that we really had to know for survival, and maybe that's why we're so sensitive to it. I don't know. But so that's dorsal columns or posterior. That's discriminative and vibratory. So let's see, what else do I want to tell you? And then we have spinocerebellar. So where is that going to and from? Spine to cerebellum. Nice and easy, right? And what do we know about the cerebellum? It does things like proprioception, right? So this is the type of information sent is proprioception, because you know that has to do with the cerebellum. So these are located in the anterolateral columns also. So proprioception, we mentioned, could be like your Golgi tendon organs, your joint kinesthetic receptors, those muscle spindle fibers, right? Those are all part of the proprioception. So those guys are sending their signals along the anterolateral columns, and it's a spinocerebellar tract, okay? And the idea is that as you guys are building on this story, go back to where you first were introduced to proprioception and make that connection of proprioception, cerebellum. Now we're talking spinocerebellar tract. Ah, that makes sense. Who were my sensory guys that were sending me that information? Oh, that was the muscle spindle fibers and the Golgi tendon. And so you make a little diagram for yourself, and you could say like spinocerebellar, and over here you could have spinothalamic. Pretend like I'm spelling it all out, and you could list the different things that you know go from one to one, because you've learned about temperature, you learned about pressure, and it was different than the proprioception stuff. So just ways to help you guys study before exam 5. All right, processing. Now what are we doing? Processing at the perceptual level. So this is the understanding of it, right? So the highest and final stage of sensory processing. Okay, so again, we broke this down to processing at the receptor level. That was the first part. Now we looked at the processing on the circuit level, where it's going into the spinal cord and up the brainstem, and who is he going to talk to? Now we're at that final, most complex part of the stage, which is the perceptual level. So this is highest and final stage. And what do I want to tell you about this? Perceptual detection. So when we say sensory processing, that's the actual perception of it, right? So perceptual detection is the simplest part. Okay, simplest part, which means the ability to detect a stimulus has occurred, right? So info got there, and before you were perceiving it, right, the RAS helped you with the perceptual detection. It decided, is this something I'm going to filter out, or is this something I'm going to make you aware of? Okay, so this is simplest and first thing that happens. Something touched you, essentially, right? Hopefully not inappropriate touching, but anyway. Magnitude estimation, all right? This is how strong or intense the event is. So how strong or intense the event is. So for example, you might just get a couple action potentials. So just a couple of things telling you that something might be whatever it's stimulating. And then versus if you're getting lots of action potentials close together, you're being stimulated more frequently, that would be the magnitude of the estimation. So how important does this information need to get to me right now, right? So, you know, is somebody touching me just a little bit, or are they going to crush my finger in a second and I need to get my finger out of that vice or whatever it is? And then spatial discrimination. So this allows us to identify the site or pattern of stimulation. So that's what discrimination, you're kind of determining the importance. So allows us to identify, I'll just put ID, identify the site or pattern of stimulation. So this depends upon receptor density. So the more receptors you have to sense this, the better that you'd be able to localize and determine where it's coming from. So for example, if there's something called like 2-point discrimination. So on your back, let's say, and you can test this on any family member or friend if they allow you. It doesn't have to be sharp objects or anything, but you could even take like a paper clip, and if you touch too close together, and maybe you're a centimeter apart, which isn't super close, they may think you're just touching them with one object. And see how far apart you have to get it before they can tell that two separate things are touching them. And how close can you get before they can't tell it's two different things. Okay? If you do that on somebody's back, you might be surprised, because how much sensory do you need from your back side, right? Where do you get most of your sensations from? The front side. Your face is very sensitive, your lips, your fingers, your hands, right? This side of your body is much more sensitive to things than your back side. Okay, so seriously, try it. You know, just take two things, put it really close together at first, or try it really far apart, and just say, tell me when you only feel one thing. And then move your two objects a little closer together, and move it a little closer. Like keep one stationary and just keep maybe moving one in, or move both of them in, you know, so that they don't get tricked and try to go, well, you're still touching me in the same spot. And then do the same thing then on the palm of your hand. You will be able to get much closer, especially on your fingertip, that you could tell that you still have two different things touching you versus what you would be able to discriminate on your back. That's what it's talking about. So you have the receptors on your back are more spread out versus on your fingers in the areas that are important, probably for survival in the past, that you can tell much more finer detail, if you will. Okay, because you have a lot more receptors, so the receptor density is higher, a lot more receptors closer together here than on your back. That's what it's talking about. Should I write that down for you? More receptors equals better location ID, identification, okay? All right, now what do I want to tell you? Processing at the perceptual level, we did all of that. Ooh, feature abstraction. So this is kind of like a weird one, all right? So feature abstraction is the interaction of several different stimuli that coordinates the perception. So we don't have a texture receptor. I know that sounds really weird, but we don't have, so no texture receptors. Okay? But we can determine, we are able to perceive the texture because of certain sensory receptors that are being stimulated and giving us the perception of what the texture would be to us. So for example, they're saying texture of marble. So like a slab of marble, we're not talking about like a little tiny marble, but let's say a slab of marble. And you might be able to get thermoreceptors so you can tell it's cool when you touch it, right? So it might be cool. It might be smooth because you can tell it's smooth versus rough when you touch it, right? And you can also tell it's hard versus something soft. So cool, smooth, and hard are three different sensory receptors stimulating your brain and putting the information together at the complex level for you to then discriminate and determine what the texture of it would be. And then when somebody says, oh, it feels like marble, you're like, I know what marble feels like. Yeah, but you don't have a texture receptor. But you gain information from other places to make that perception of what it would feel like. Okay, so pressure receptors telling you it's hard, tactile receptor telling you it's smooth, thermoreceptor for it being cold. So these are a combination of stimulus of various sensory receptors. So combo, that's the coordination of perceptors. Combo or coordination or combination of stimulation of various sensory receptors. Very cool. All right, awesome. Now, nerves and ganglia. So when you see nerve, you should think PNS, right? And ganglia, what do you think? Definitely you should be telling me PNS, right? So nerves and ganglia, PNS. We have, what were they called in the CNS? Those other things, yeah. All right. So, so do you guys remember when we talked about muscles, we had different mesomes, the different CT layers? Well, you have the same thing when it comes to nerves, okay? The nice thing is once you knew mesomes, neuriums are not that hard. And neurium, you know, it means nerve, myo for mesium meaning muscle. So what we have here is, let's see. Oh, and also just like muscles, you have fascicles. So cool, right? So bundles of axons, axons being the nerve part, right? Just like in skeletal muscles, we have fascicles. And the fascicles being put together are surrounded by the perineurium. When you have a bunch of fascicles together, then you would have the outer layer would be the epineurium, epi upon, peri around. And then there should be here's an endoneurium. So one single axon would have endoneurium around it, right? So there's your axon. So not too bad, right? You guys have seen this. It's not going to be anything scary then. On here, they're showing you like one bundle here. One fascicle is surrounded by what again? Perineurium, right? Okay. And then each axon would be individually within the fascicle would have endoneurium around it. So that's all they're talking about there. Let's see. Already said that. If we're looking down here, they're saying, you know, if you look at this one thing, that is one nerve. Here they did the same kind of picture that we did up above. And the cool thing is they took that dorsal root ganglion, the little bulge here on the dorsal root. Here's the dorsal root ganglion. They're kind of showing it off a little bit there. And all these little guys with the little heads there, who are those guys representing? Your unipolar cell body, right? Because they live in the dorsal root ganglion. So that's all that part was showing you there. Lovely picture, right? And you guys already know where dorsal root ganglion is and everything. Let's see. So getting into terminology, we have a nerve, which is a bundle of axons in the PNS. Because remember, in the CNS, what do we have to protect our CNS? We have bone, right? We have bone, and then it's covered by our dura mater and things like that we talked about. But these guys out in the periphery, all these nerves and this nerve tissue, who's protecting it? Bones? Right? So it's the CT that has to protect these guys. So this is tough CT. It makes the nerves tough also. When you guys get a chance to this week, after your muscle eval, you guys will be doing the cadaver demonstration, and check out what the nerves look like in the cadaver, and you'll see how tough and strong they are, okay? So these can be myelinated or unmyelinated, just like before. So they are surrounded by CT, which you just saw in the previous picture, and they can be myelinated or not. I'll just be quick on the notes there. And who is our cell that's doing the myelination in the PNS? The Schwann cell or neuroleukocyte. Good, good, good. And ganglion is a cluster of cell bodies in the PNS. These are also wrapped with CT. So if you look back up here, this has a CT wrapper around it here as well. That's what they're showing you, okay? And so the terms there are what we just talked about: connective tissue wrappings of a nerve. Endoneurium surrounds the individual nerve fibers or the axons. Perineurium, peri is around, so it surrounds the bundle of fibers. This is the fascicle that we said, just like on the nerve, on the muscle cells, skeletal muscle. And then we had epi, epi means upon, so this is covering this is the most outer layer of the entire nerve or bundle of fascicles that got mushed together, right? So that's the outside part of the nerve. What else do I want to tell you guys? Okay, that looks good. Yep, yep, yep. Or you could say, instead of bundle of fascicles, what else could you say? Bundle of axons within the fascicle, right? So that would be accurate too. So types of nerves. Some nerves are sensory only. So for example, eyes are, if you look at cranial nerve number 2, it's only sensory information coming in, okay? Because the motor of moving your eyes around, that's muscle. So it's not the eye itself, okay? Olfactory, cranial nerve number 1, is also sensory only, right? Sensing the sensations of smell. And again, we talk more about that in later, but that means, would these be afferent or efferent fibers? If it's sensory, it's always afferent, right? Other nerves are motor only. So are these afferent or efferent? Efferent, okay. And then we have some that are mixed nerves. So that means they contain both sensory and motor axons. Information's going both ways. And if you guys remember, when I came up to this picture here, here's a nerve example, right, that came down like this. It had both sensory info coming in, motor info going out. So I drew a mixed nerve there, correct? Yeah. All right. And so if it's mixed, is it afferent or efferent? Both. Yes, thank you. Awesome. And guess what? All spinal nerves, it says most nerves are mixed and all spinal nerves are mixed. So most nerves are mixed and all spinal nerves are mixed. Okay? So that means all spinal nerves must be afferent and efferent fibers, right? If we look at ganglia, which again, whenever we say ganglia, you're thinking PNS, right? Okay, so afferent is the dorsal root ganglion, so it's always sensory and always somatic information. Okay. Efferent, we're actually going to talk more about in the next chapter, but these are part of the autonomic nervous system, and right now we're just doing general PNS stuff, but autonomic nervous system, and it's talking about prevertebral, paravertebral, and terminal meaning the end or output part of it, pathway. So, but again, we'll talk more about the efferent and autonomic nervous system in the next chapter. And regeneration of nerve tissue is possible under certain circumstances. Oh, we can repair some stuff. So the CNS, could we repair things? But in the PNS, we can. That's why if you go in for a surgical procedure and they make a cut, They have to cut through some nerve fibers. And after a while of healing, if the fibers are close enough to be able to approximate and match the other side again, you'll get your sensation back. But maybe for a time while you're healing, you have like a blank area, you're touching it, but you're not sensing anything because the nerve didn't make the connection and can't send that stimuli up to the brain telling you that you're being touched in that spot. When it finally heals, if it can heal, then later you'll be able to touch. And now sometimes you may never be able to touch it, right? Maybe if scar tissue gets in between that axon, it's not going to be able to get information through the scar tissue then, but just depending on where it is, location, things like that. So let's talk about repair steps. So repair steps after an axon has just been damaged. So this just happens. So let's say we have cut ends. It will, on the proximal part, seals spontaneously, okay? So that's kind of cool, right? And let's see. Here's our picture. Here's where they're saying there was trauma. So some sort of sever or cut or something happened. Could a nerve get overstretched and tear? Yeah. Yep. So whatever happened, it damaged and severed something here in this axon, right? So it didn't totally damage things because the cell body is still intact. Where's the cell body located? Dorsal root ganglion, right? Up by the spine. So this is out on the axon, and look where they are showing us. So what do you guys think this stuff is right there? Skeletal muscle. So this is a neuromuscular junction, right? On the axons that are making contact with the skeletal muscle fibers there, okay? And so, so this would be, if we're going to tell a muscle what to do, is this afferent or efferent nerve? It's an efferent nerve because it's going to tell the muscle what to do, right? So if this had been a sensory receptor, it's the exact same story though. I'm just pointing out that this is efferent because it's talking to a muscle. Effectors are your glands, your muscles, right? So if this had been a sensory nerve that got severed, it's the same things that would happen. So just understand that. So the nerves are multipolar, has a neuromuscular junction. Is it myelinated or unmyelinated? It's myelinated, you can see that. And what cell myelinates the PNS? Schwann cells or neurolemmacytes. They're separated by what? What do we have here? And here. And here. Nodes of Ranvier. And remember, that's what helps speed up the process of sending this information. So if you get a cut or you get traumatized, it's saying that it will seal off the proximal end, right? So that's what it's saying here. The proximal portion of each severed axon seals off and swells. And the distal portion of the axon and myelin sheath degenerates, and the neurolemma, though, survives. What's the neurolemma? That was the myelination around it. Okay, so the myelination is there. The nerve, we sealed it off though so that we can try to repair. And it's saying that the axon distal to the cut dies. They call that Wallerian degeneration. And the macrophages are going to come in and clean up the degenerative part of the axon there. Any debris in there that we need to clean it up so we can have a fresh start and try to regrow our nerve. But guess what? We have a tunnel to grow it through, which is our neurolemma, right? So it knows where it needs to go to still. If that had been damaged also, or to the point where it didn't seal off, then you might have a nerve not make it to where it was supposed to go to either tell something to do something or get sensory information back to the CNS. But that would then be like the example of you have no sensation still there, or you can't make that muscle work, and eventually it would atrophy and shrink down and stuff, right? So, so macrophages will clean up the distal debris. Because what do you think swollen means? The macrophages are in there and they're cleaning things up, right? Macrophages clean up distal debris. And didn't quite get to the end there, but I'll say it really quick and then we'll review this when we come back. So the Schwann cells form a regeneration tube to guide the axon sprout back to its original site. So that's what they're trying to show you here. Okay, so we got a little sprout there. Schwann cells stay in place because of the endoneurium. The Schwann cells secrete actual growth hormone factors for axonal sprout to occur. So we have other things telling it how to do this. The growth rate is only 1.5 millimeters per day. So it's a pretty slow process. Go look at a ruler and try to figure out 1.5 millimeters. It's only going to go that per day, okay? And then they are remyelinating themselves. Do you guys see that? They're going to start, the Schwann cell or the neural lemmacyte's going to spin around there and continue to grow and create a new myelinated area there. And the farther the damage is from the cell body, the more likely successful repair would be made. What they mean is, if you got cut at your finger versus up here on your brachium, okay, the finger would heal easier, faster, because it's further away from the body. Think about if you had to heal something from here on your brachium all the way to your fingertip. That's going to take way longer and be less likely to happen. That's what it's saying when it's saying the farther the damage is from the cell body's up by the spine, dorsal root ganglion, the more likely successful repair would be made. If the sprout has to travel too far, it could escape from the tunnel and get into surrounding tissues, and that could be something called a neuroma. I can talk about that again later if you've never had a neuroma in your foot. And then it says CNS axons do not repair. We know that, right? So oligodendrocytes do not form regrowth tunnels, and they release growth inhibiting factors. And do you guys remember, brief review, who the cell was that replaced as scar tissue in the CNS? Astrocytes, yeah. So this is a good stopping place. I went a minute over, and good job, guys. Woohoo! And we'll start cranial nerves on